About 4:15. Nah, 3:15. 20, where's 20? 20 is there. Just before the 8. Page 42 to 54. Matter waves. Summarizing page 42. Rutherford Bohr models. So it's the model of the atom. How is the atom constructed, or what is its structure? Quantize. Light energy was quantized. Light. Atoms, light, charges, Bohr. Planetary model of the atom. Chemical organization of elements, atomic number, nuclear protons, neutrally charged neutrons. 42 atoms. Structure. Electrons, protons and neutrons. Orbits. That's the electron orbits. So it's the atomic structure, Rutherford Bohr. So it's about the atom and how it's internally structured. What is its internal machinery like? So 43, decay, chemical reactions, nuclei, something about size, grain of sand. So it's something about radioactivity and size of the atom. So maybe that's what the Rutherford was doing, that he came to the conclusion that the atom is mostly empty space and matter is mostly concentrated in a very small nucleus. Maybe that's the story. Then it's Bohr orbits and momentum quantization. When you start out, be careful. Go slow, go slow. If you start a race too quickly, you're not going to last. So start slow and build up. So be sure that you tune into the process. The pause button. I should have pressed the pause button again. So my watch is not going to be accurate. but I can see here on the screen how long it's been running. Oh, but I've got two. Alright, but that's not important. Two files. This file, I can see how long it's been running, this recording. Atomic structure. Some days you are just slower than other days. As long as you realize it, it's fine. Atomic structure, orbit, size of the atom, orbits and momentum quantization. The quantization doesn't come into this section. I don't know why it's mentioned here. Electrostatic acceleration, electron acceleration. That's the story of the emission. As if electrons accelerate, you get emission and it loses energy. Force, electrostatic force. Where are we now? Page 44. Ooh. Force and acceleration. Electrostatic force and acceleration. Maxwell, electrodynamics. So it's losing energy. That's the electron that will lose energy then. Electromagnetic energy. Theory, emissions of light. Spectral lines. It's the atom that under certain circumstances emits light. Previously we've been talking about the structure of the atom, so they are trying to explain how can the structure produce these spectral lines. And then Bohr comes into the picture. Bohr orbits. In Niels Bohr. I'm getting the impression when I get to more difficult chapters, I'll have to read them several times. These sort of theories still. I've studied it, so I know it, but the later chapters I know about nothing about. And I suspect I'll have to read those chapters several times to understand what's going on there. Build my knowledge slowly over time. Not radiate EM energy, stable orbits, electrons, stable orbits. Stable orbits. Niels Bohr's model of the atom. So orbits, photon emission. There's photon. Wait. Here's something about quantization. The angular momentum of an electron in each orbit would be quantized in units L equals NH, where N is an integer and H is Planck's constant. L angular momentum in spectral line emissions formula. So what is going on here? So this is, I think, that only certain angular momenta is allowed. And that shows when the electron transitions between the orbits, you get the photon energy difference and photon emission or what. Today is slow. Angular momentum. Let's go on. The problem with diagrams like this is there's a massive amount of information. A picture is worth 1,000 words, so this is several pages actually. It's now 46. Something about energy, electron volts. Electron volts, something about electron volts, energy. Single photon. The photon's energy. There's the energy levels in the atom. And the transitions between the various energy levels. Ionization, continuous. Energy levels in electron volt. N equals 1. Blah 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 till infinity. Absorption, emission, ionization, electron transitions. So that's the emission of light and the electron transitions between the various energy levels. Ionize, hydrogen, orbits, orbital shells, different shells, electron shells. Something about ionization. That's when the electron gets free. It's freed from the atom. Different shells experience central positive charges. 47, 48. Oh, 58. Electronic structure. What? I think this is the part where things get really. Electron, magnetic field, charged particle, Maxwell. Something about mass, electromagnetic field, Newtonian matter, measured mass, mass of the electron was somehow a product of its electromagnetic field alone. What? If the mass of an electron was somehow a product of its electromagnetic field. Ooh. I think electric charge, forces. Not really relevant. Electric field of an electron. Mass. Electron mass. Mass forces. Ooh. 49. This idea turned out to be flawed. Einstein's theory of special relativity, motion of the observer, moving, shifting, that's Stalling field. Electron structure. Electron structure. What do they mean? The electron structure. And relativity. Compton radius of the electron. So its size and matter. Mass of an electron with speed. Speed, mass. So, electron structure. So its mass and size. I think something about they're looking at the electron. What is going on with the electron? So we've Bohr brought us the what's it, 13 minutes. The orbits and the electrons transitioning between the quantized orbits, producing the spectral lines. Physical dimension. Not of electromagnetic energy. Mass and charge. So it's they're really battling with the electron. Outside the atom, electrons could create continuous electrical currents that produce magnetic field, but inside the atom, electrons were in some way the midwives to the emission of discrete spectral lines. Outside the atom, you've got electric current and magnetic fields, but inside it, you get that jump between the various levels, producing the spectral lines. That's what's being discussed here. Electron inside, in and out of the atom, in jumps, or whatever you want to call it, transitions, and out it's electric, it's current plus magnetic field. So that's the EM behavior. And then we go to matter waves. We're finally at matter waves, page 50. 15 minutes. Drinking some tea. Matter waves. Finally. Spectral line, laboratory condition, light, wave light such as interference and diffraction, contradictory pictures of reality. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomenon of light, but together they do. So it's light, waves, and photons. As soon as I've written something, I'm satisfied. Maybe I've understood something. So this is the story about, what's his name, Louis de Broglie. What he did really impresses me. That's I should tell you what I'm reading. Electrodynamics thesis, coexistence of the wave and the corpuscular aspects, light quanta, two key formula. Through a simple mathematical manipulation of two key formula, de Broglie discovered the momentum of a particle. So de Broglie momentum of a particle. P equals mv and E equals h, and the frequency is speed over wavelength, and then you get the wavelength equals Planck's constant divided by p. So it's momentum. Speed, mass, momentum. Using the Broglie matter waveform of Planck's constant, we get a wavelength of so many meters. There is apparently no obvious limit to this matter wave effect, which can be applied to macroscopic objects. So that's the matter wave. And that's the momentum. Some associated proposed that matter had wave-like properties. That's the most brilliant suggestion of all of this quantum theory. Matter wave-like properties. Oh, 51. Now that is quite a jump in understanding. Should read his thesis and see how he came to that. Page 52. Where are we? We had started a new file. Yeah. Somewhere it's going new recording. The Broglie's, the matter waves, a guiding matter. Matter waves guide the matter. Matters were actually guiding matter to behave as wave-like objects, but were not themselves waves of matter. Guiding waves. Slow moving crystalline X-rays, wavelength, molecule, atoms also confirm this matter wave effect. Orbits of an atom, improved model of the atom. X-ray crystallography, X-ray. That's electrons. Slow moving electrons. So, matter waves guide the I'm thinking too much by myself. I should try and communicate while I'm reading. Electron diffraction. By crystal structure. So there they base it on. They know about diffraction. It's a regular pattern, and that regular pattern gives you diffraction of waves. That diffraction pattern, and they observed it also with electrons, which tells us there is some wave behavior associated with the electrons. Now we come to orbits. Integer number of wavelengths around electron orbits. Integer number of wavelengths in the orbit. The wavelengths need to fit. That's the allowed orbits. Atoms to be found only in certain lanes where the waves do not interfere with themselves. So it's a continuous path it can follow. Interfere with themselves. Whoa. Quantization condition. Matter waves, little quantization. Okay. Angular momentums or orbits. Only certain orbits are stable. Angular momentum is quantized. And that's the final page. Do I want to do something here? Bohr model, momentum quantization spectrum, the Broglie matter waves, structure of an electron, both particle and wave, electron diffraction. So that's a summary of all this previous information actually. It just summarizes the previous pages, these key points. And there is my little notes. Okay.